So what I want to talk about today is something called filament models. And it's the kind of simplest model you can make of a chaotic, of what a chaotic flow effectively does, even though this is not at all chaotic, or at least not in the sense that we usually understand chaos. So it's an example of a good mixer, so a good mixing flow. And it's something that probably many of you have seen before. It is the famous hyperbolic stagnation point, where you just have a flow whose streamlines look something like this. And so the flow itself can be written as u of x. T is some constant lambda x and the same constant minus lambda y, where lambda is called the rate of strain, and it's got units of inverse time. And so, as you can see, there's a fixed point right in the middle. But other than that, there's a direction called the unstable direction along which things exponentiate away from the fixed point. And the perpendicular direction, the y direction, things exponentiate towards the fixed point. Okay? And so the question is, what would it look like if I put a little patch of concentration of something in this flow and watch the evolution? And you'll see that even though it's a very simple flow, it is very instructive to look at the solution. Basically, once you've solved this, you can even interpret lots of pictures that you look at involving mixing. So the advection diffusion equation, oops, broken chalk. Now it's like this. So u dot grad looks like lambda x dx theta minus lambda y dy theta. By the way, of course, this has to be the same lambda in order that div u be equal to 0. And so the equation you want to solve now is Laplacian theta. Oops, actually I'm going to use kappa because I used kappa in the last lectures. I just realized that I keep switching between kappa and d. So let's just stick to the same thing that's in my notes. Otherwise, I'm just asking for trouble. So it is actually possible to solve this pretty much exactly, though it's a little bit of a tedious thing. And again, in the interest of understanding what's happening without getting bogged down in details, there's actually something very clever that you can do. With some foresight as to what the end solution is going to look like, I'm going to look for a special type of solution. I'm going to look for solutions that do not depend on x. And we'll see later why that's actually a reasonable thing to look at. And then, in addition, we'll just assume that there's some exponential time dependence to the solution, because that'll turn out to be the natural thing to do. In other words, this is very much an ansatz. As usual when solving partial differential equations, very often the solution method involves the fact that you know the answer. So somebody in the 19th century must have hit their head against this, but once that person found it, probably French, right? Then we don't have to work anymore, right? Okay. So if you insert this ansatz into this equation, the ddt's, of course, just return a minus lambda, and then there's no derivative on f. Then the y direction still appears because there is a y dependence to my flow, but the x dependence goes away completely because I've just not put it in. I'm basically doing a one-dimensional model. And then on the right-hand side, the Laplacian just becomes a second derivative of f. Okay. So now, I did not tell you boundary conditions. So in the previous lecture, I used a bounded region, in which case I could define things in terms of integrals over all space. You have to be a little careful now because we're going to be on the open plane, and you have to be a bit careful about the convergence of your integrals. I'm going to sort of not worry about this too much. So I'm going to assume that the boundary condition is that f goes to 0 as y goes to plus or minus infinity. But immediately I can't really define integrals the same way as I did last time because the x direction being undefined will lead to divergent integrals, right? Because things don't depend on x. So you have to find a restricted average in the y direction only in order for this to make sense. But again, this is very much because this is a model. In practice, maybe let me give you a bit of foreshadowing. Reason why I can use this y solution is that the evolution of a blob in this flow would look something like this, right? If I put a dot of dye, it will go towards the origin, or if it's already straddling the origin, then it'll just start and stay there. Maybe it'll remain centered on the origin, but then it will stretch out and compress. Actually, my picture is not very good because it should be getting thinner because it's compressing in this direction. So the fact that we're neglecting the x dependence means that we're assuming that it's already infinite and it's already stretched all the way. So in practice, these integrals would converge, but the value would be cut off by the width of your finger, of your thing, which would be time dependent. Okay. Right. So this has a nice solution. Probably some of you might have already guessed the solution. Whenever you get a non-constant coefficient equation like this, right, where one of the things has an extra y, probably you're going to get some kind of Gaussian-looking solution, and that's exactly what you get. So the solution is f of y is equal to e to the minus y squared over 2l squared, where l squared is a length, a squared length, defined as kappa over lambda. And this length scale, L, is your best friend. It is the thing that is the most useful to characterize a mixing pattern in a way. So this length scale is exactly characterizing the width of the striations in your coffee cup when you start to mix. Of course, the striations eventually go away, but in the filamentation process, it describes the length scale of the finest filamentation that you can observe. So, in other words, if I go back to my original equation, then my original variable, or sorry, function, then the solution looks like this. And so you can see that I'm going to get a mixing pattern that will decay exponentially in time, but will achieve a completely spatially constant form. In other words, the picture of my solution now is exactly of an infinite filament of a fixed width. And the half width of my filament is L, right? Because it's a Gaussian form, so the standard deviation, or the half width, is exactly L in my expression over there. So that's kind of interesting already, right? Because this flow is heavily compressing, it's exponentially compressing, and yet it achieves very rapidly a steady state where the solution is actually completely time independent, except for an overall scale factor. In other words, the picture doesn't change, but it gets dimmer and dimmer and dimmer with time very rapidly. Okay? So what's happening is that this is the dominant kind of balance that you see when you try to do mixing. It is a balance between some kind of exponential stretching and the exponential action of diffusion, which is pushing against the fact that you're trying to compress this concentration field. So, in other words, this flow, if there was no diffusion, would make this filament infinitely thin. It would just keep getting thinner and thinner exponentially. But diffusion doesn't like that. Diffusion is a process that wants to broaden the distribution. So eventually they all agree on a width, and that width, of course, you could have guessed at this width, of course, because there's only two parameters in the problem, and there's only one way to make a length out of them. So it's the natural length scale in the problem. Okay? So this has a name. It is called the bachelor length, or the bachelor scale, depending on who you ask. Okay? And it's the characteristic length scale of an advection diffusion process that involves some kind of rate of strain. It isn't always true that there is such a length exactly defined in this way, but whenever there's some kind of exponential stretching action in your flow, there will be such a length around. Okay? And notice, by the way, that everything is as I advertised in the last lecture. This length scale is proportional to the square root of kappa. So the gradients that you create in your flow are of order 1 over L, or 1 over root kappa. So remember the last time I discussed how in our advection diffusion equation, when you considered the average of the variance, right? So the variance of the concentration, assuming that you got mean 0, which you can usually do. Remember that our equation was something like this. So we're exactly in a situation where the gradients of theta provide exactly the compensatory factor to overcome a small diffusion. In other words, for this flow, grad theta squared is exactly of ordered kappa inverse, and so the decay of the variance becomes completely independent of kappa. Okay? So this is exactly the prototypical archetype of a good mixer. It's remarkably simple, of course, but I think that, you know, understanding this case allows you to understand lots of things. So now the question comes, in a real flow, what is lambda? Well, lambda has many different kind of interpretations. If you believe that the local rate of strain in your flow, which you can measure by, if you've got the velocity, you can take the gradient of the velocity and you've got your local rate of strain, then actually people actually make this kind of ansatz that if things get balanced quickly enough between this equilibrium to diffusion and stretching, then you can actually use this to back out some properties of your flow. So for instance, I mentioned last time, in oceanography, you get these patterns of phytoplankton that you can see from satellites, and these patterns often involve, you know, these are rather large. Often you'll see a picture of Iceland, you know, on these satellite maps. So we're talking roughly Iceland size, okay, if that gives you a sense of scale. Usually maybe even bigger than that. These are called plankton blooms, and they occur seasonally in the ocean. And you'll often get a filament being drawn out of these patches. And oceanographers love to kind of speak of the rate of strain and the balance of diffusion and kind of back out a bachelor length out of this based on the filament. I think this is a bit of a wishful thinking to expect that everything should work out so nicely, especially because also three-dimensional processes can alter the width of this filament. It's not true that there's just a two-dimensional dynamics. There's upwelling and downwelling in the ocean, which will modulate the width of this filament in a very interesting way, actually. So in other words, the filament has some three-dimensionality under the surface, which has an interplay with the horizontal scales. And that in itself is a topic that, you know, studying exactly the shape of this, even of this simple solution when dealing with three-dimensional flows is actually quite interesting. And people have done some work on that. Okay? Any questions? So, by the way, there's a nice way to predict e to the minus lambda t. Yes? So, you mean, well, diffusion, of course, wants to spread out. In fact, I'll talk about that in a second, about effective diffusivity, but diffusion in general, if you start with some particles, the particles will want to spread out diffusively. Okay? How is? So I was just about to point that out. That's a very good point. So, you know, if there is no diffusion, the area of this patch is preserved. Okay? So now think of the finite extent patch. It has some area, and if there were no diffusion, it would be preserved. But of course, there is diffusion, and that changes the area of this patch. So let's compute the area of this patch. Well, at the end, the patch has width L, right? Where L is the bachelor length. And what is the length of the patch, roughly speaking? Right? Sorry? Not infinite. I mean, like, if I don't use my solution now and I just think of from the initial value problem, what is the typical length of this patch as a function of time? No. Actually, it doesn't depend on kappa, right? It's just the rate of stretching in this direction. Trajectories, fluid trajectories in this horizontal direction just kind of exponentiate away from the origin, right? So the patch, the extent in this direction is e to the lambda t, roughly speaking. Okay? So therefore, that means the area of the patch is of order e to the lambda t, right? Because it's L e to the lambda t. So the area is L e to the lambda t, right? Now, what is the total amount of theta of concentration on the patch? Well, diffusion, neither advection nor diffusion create or destroy the concentration field. So in fact, the total amount of theta is fixed on the patch, right? So the concentration at a point then should be equal to the total amount of theta, right, divided by the area. Right? If I try to evaluate, again, this is a very crude calculation, but assuming all things being equal, you could measure the concentration by a point by saying there's some total amount of theta there, and it has a certain area, so on average at a given point, I expect to find some value of the concentration, but this is a constant dividing by A, so this is as e to the minus lambda t. In other words, the concentration at a point should decrease roughly as e to the minus lambda t, which is exactly what we find from the exact solution of the problem. Okay, so that's also a very useful kind of rule of thumb often. If you can compute the area of a patch, right, as a function of time, that's often a very good indication of how much concentration you'll find at a given point and how it evolve. Okay? You can back out the kind of point-wise concentration from this. But again, this is a very crude rule of thumb, but, you know, if you're an oceanographer, very often all you have to work with are satellite pictures, so crude rule of thumbs are actually quite useful to actually get some numbers out, right? Okay. Questions so far? There is diffusion. Kappa is non-zero. That's right. That's why there's an L. If kappa were 0, this length here would be e to the minus lambda t. And so the product of the two would now be 1. And that's the statement that area is conserved, right? But in this case, area is not conserved. The area is growing linearly in one direction, but not in the other. By the way, this calculation is even more useful than you think because it also worked perfectly well in 3D when the value of lambda has different values in different directions. You can use this exact argument to compute the point-wise decay. So it's a very general argument and it works very well. It's a very nice rule of thumb. Compute the area or the volume of your patch, assuming that the concentration is fixed. So basically 1 over the volume is the... In 3D, actually, I'm not going to talk much about this, but in 3 dimensions, you have 3 lambdas to work with, right? And div is 0, so they just have to sum to 0. But that could be in a sum combination. It just tells you that one of them is positive and one of them is negative. The one in between can do either things. It can be positive or negative or 0. If you have 2 positive lambdas, that corresponds to a... let's see, what's the shape that corresponds to in 3 dimensions, right? You're stretching in 2 directions. So it's actually a pancake shape, right? So you're stretching in 2 directions and you're compressing in 1 direction. Whereas if 1 lambda is positive and the other 2 are negative, then that's a 3-dimensional filament because you're compressing in 2 directions. But this argument would work perfectly well. It would allow you to predict exactly the rate of decay just based on computing the volume of this filament. So in one case, it would have 2 directions that, you'd have 2 bachelor lengths, right, corresponding to the 2 directions. Yes? A what? Yeah. This is an unstable fixed point. Well, you have to respect div u equals 0. Of course, you can mix arbitrarily well if you allow div u to be non-zero, right? But if you want an incompressible fluid, which is usually what water is, then you're constrained by that, and this is the most unstable you can be, right, in this way. You can't have a repeller or an attractor in incompressible flows. Yeah. Otherwise, you can be arbitrarily good at mixing, absolutely. So, in fact, that's a good point, right? A mixing, it's a battle, right? Div u equals 0 works against you to some degree, and the battle is how to overcome that. Anybody could mix if you were just allowed to take the fluid and compress it down to a point, right? That would be very well mixed very quickly. But incompressibility doesn't allow you to do that. Okay. Okay, good. And just to remark, last time there was a logarithm that showed up. So we can ask, how long will it take for this solution? So here I'm already starting at the steady state in a way, right? So But in practice, I would have an initial value problem to solve, and I can ask how long will it take for me to settle down to this solution? Well, the answer is it's the length of time that it takes for my patch to be compressed down to the length L, right? And so if you think about it, you have the length L. If I initial width, right, let's call it W, I want W e to the minus lambda t to be equal to L, okay, where W, let's call it W0, is the initial width of my patch. It gets compressed down, and eventually it reaches the bachelor length. And so now if I solve for t, I can take a logarithm right, log L. And so t is equal to, by the way, this is, I guess it's log L over W, let me rewrite it as log L over W0, right? So I would get lambda t is log of W0 over L. And then I would divide by lambda. And so that's the time that it would take me to reach the length scale of where I balance advection and diffusion. But again, that's exactly what I claimed in my graph last time, that there was a typical mixing scenario as a function of time, was to have a plateau where initially you don't feel diffusion, but eventually you've compressed using whatever stretching is happening in your flow. You've compressed down to let's call this TD for T diffusion. You've compressed down your patch to a level where it starts to feel the diffusive action of the flow. And after that, the decay rate tends to be, in the ideal case, the decay rate tends to be exponential at some fixed constant, but that constant itself is independent of the diffusivity. Again, the solution itself depends on the diffusivity, but the rate at which it decays is independent of the diffusivity. Okay? So it's all due to the balance between advection and diffusion. That's really at the heart of the matter. So this is the logarithm that I was mentioning. And by the way, this is also what makes mixing so effective, because it means that no matter how small L is, it doesn't matter because it's only a log, right? So it's always relatively easy to overcome a logarithmic dependence. So that's why it works so well to stir your coffee, because, no matter how small the diffusivity is, you might have to do one more flick of your hand, but you'll get there fairly rapidly anyways. It doesn't really matter. W is the initial width of my patch, thinking one-dimensionally. So I'm assuming that my patch starts wider than the bachelor length. It would be a bit strange at the scale which is below this bachelor length. I mean, it could happen, but then the filament would actually have to expand out, right? That would happen if the diffusivity was large, but it's not the typical scenario. When the diffusivity is large, you always have to ask yourself, then why are you stirring, right? You don't need to. Yeah. So typically the scenario is the diffusivity is small. Okay. Other questions? So now that we talked about filaments and widths, in this cartoonish picture of mixing, let me introduce another way of looking at mixing, which is this so-called effective diffusivity. And this relates a lot to the lectures that we're hearing so far by the other lecturers. It's a much more stochastic view of the world. And I'll give you some theory relatively quickly, and then I will show you some examples on the computer where we can actually see the action of some of these flows. So the idea of an effective diffusivity is a very different viewpoint than what we've done so far. So far, we took this equation and we directly kind of attacked it and tried to find theta as a function of time and kind of interpret the solution in terms of, say, looking at how the variance of the concentration varies with time. The idea of an effective diffusivity is instead to derive a reduced version of this equation, exactly in the way that Georg is talking about, and he'll probably do examples in the same spirit as this one, if not exactly like this one. I'm not going to do it rigorously, but the idea is to obtain a homogenized version of this, as it's called. So here I'm going to use capital theta to mean a coarse-grained version of my theta. In other words, theta, because it contains, it might be some complicated, little theta might be some complicated concentration field, including the action of the velocity field, which makes filaments everywhere. But then I'm going to write a so-called homogenized version of this, which is an effective diffusion equation for some coarse-grained variable. So here, capital theta, given this noisy concentration field, would just become some kind of, usually it's a kind of ensemble averaged. When you're lucky, you can get away with spatially averaging if things are kind of self-randomizing enough. But usually it's in an ensemble sense that this is an effective equation. Sorry? Yes. Yeah. That's right. Yeah. What I mean is that you're doing a coarse measure of how this pattern is spreading, kind of ignoring the small-scale details. You're averaging over them in some sense. And then you're obtaining an effective equation called often a homogenized equation, which has absorbed these small scales. In particular, the diffusion term is now gone completely, and it has been subsumed into an effective diffusivity. And so what you get is actually a normal diffusion equation, or a heat equation, where the diffusion constant is now not the molecular value, but something that's been enhanced by the velocity field. Okay? And as you might imagine, it better be that this effective diffusivity is larger than the molecular value, right? Otherwise, you would be in trouble. So typically what happens is that, yes, the velocity field here appears in some sense in this effective diffusivity, but it increases it. It makes it larger. Okay? By how much is the interesting question. Okay? And I still haven't quite decided where I'm going to go after this lecture, so I may do a kind of more mathematical approach to doing this problem, or I may do something else, depending on the feedback I get from all of you. But today I'm not going to do a rigorous derivation of this equation. I'm going to show you systems where we can kind of eyeball what the effective diffusivity is based on just visually looking at what's happening. Sorry? Yeah, so you have to use a different variable because capital theta is a sort of smoothed version of little theta, right? So it forgot some of the information about the small scales. It's like what Georg was talking about today. His fast and slow variables were in time, but here the fast and slow variables are in space, right? There's some fast oscillations, and you want to ignore that and just consider some local average over these fast oscillations. Yes? Yes, exactly. Absolutely. The cell problem may or may not be time dependent. That depends on the particulars, right? Usually if your flow is steady, then the cell problem is not time dependent. So the noise in the problem, that's what we'll see on the computer simulations. The noise in the problem can come from many, many different places, but it doesn't have to be stochastic, right? As Georg was pointed out, there are some deterministic systems that have a very nice stochastic reduced model, and that's exactly what I'll show today. It'll come from chaos, basically, right? So chaotic advection, which creates large gradients, etc. Everything is perfectly deterministic, but because there's some sensitive dependence on initial conditions, the concentration field will get complicated fast enough that it essentially can be well approximated by some average process. Yeah, usually there's some periodicity assumption. You can relax that to some degree, but yeah, usually, as you said, there's a cell problem and you assume periodicity, etc. But as I said, I'm going to be doing it in a very kind of hand-wavy way today. I'm not going to do the mathematics of this. We're basically going to run some simulations and fit an effective diffusivity. Hopefully I'll have time. Yes, I have plenty of time. Yeah. Okay. All right, so that's the main framework. Let's just derive a quick explanation of where effective diffusivity comes from. This is going to be a little bit primitive compared to what you've been hearing from the lectures, but I just want to kind of solidify the point of how an effective diffusivity actually occurs in a kind of simple example. So typically, the idea is that you have some process, which I'm not going to define very rigorously at all, but let's say you're following a particle in your fluid, and maybe there's some map which has some randomness to it. I'm not going to use the stochastic differential equation notation. I'm just going to write it in terms the way the physicists often do. We're just using the variables with no differentials in front of them or anything like that. I'm just saying there's a map, and the position of my particle at some step, so I'm going to discretize time here, is just some wherever it was at the previous step, plus some noise term, xi. Okay, so this is going to be the noise, which will correspond to the action of my flow in some sense. So you can solve this explicitly, and you get that it's just the sum over all my steps, of course. Here I've got a typo in my notes. I guess that should be an I. Right? So basically, the position of my particle after n steps is just going to be the sum over all of the noisy bits that I've added. And I'm going to use the angle brackets to denote an average. So an average over my random variable xi. Again, this is all very sketchy. It's just meant to motivate a little bit what I'm going to show you on the computer. And by the way, these are going to be ID, maybe even Gaussian. It doesn't matter too much because I'm only going to be talking about, it's just going to have finite variance as far as I'm concerned. I just want to show you how the diffusivity comes into this. So the way I would compute the diffusivity from particle description like this, instead of using a partial differential equation like this, is I would just use, some educated knowledge about what a random walk looks like, right? This is basically undergoing some random walk, could be in multiple dimensions. So I know that a random walk will I'm going to take, I've taken a centered random walk whose average is 0, so my particle on average goes nowhere. But that motivates looking at its mean squared displacement. And so if I square the right-hand side and then take some expectation values, this doesn't matter at all because its average with respect to the xi's goes away because the average of the xi's is 0. Sorry, I forgot to say that. Of course. So if you square this, only the squared terms survive when I take the average, and they're all the same. So I get n times the, first of all, let me do one step. I get the average over the squared of these variables, but then I've declared them to be Gaussian, so each of these is going to be some width of my Gaussian, so some standard deviation or some variance in this case. And I've got n of them, and they're all identical, so I can write them just as n times sigma squared. Okay? So again, that's the mean squared displacement of my particle after n steps of whatever process this is. But then I can actually use this to back out an effective diffusivity. Because I just use the usual definition of the fact that as a function of time, the mean squared displacement grows as twice times some diffusion constant times t, where t is some time. And then I can just use the fact that my time is n times some period between each of these steps, right? And then I solve for kappa, or for k, sorry, and I get that k is sigma squared over 2t. Sorry? Oh, the period between these discrete steps. I'm assuming that I'm sort of hitting this particle at discrete times n, but in the world there would be some time between these discrete times. Of course, this could itself be a random variable, right? It could be Poisson distributed, so that would, then you would have to modify this calculation here for the fact that the number of steps, if you fix the time, the number of steps happening in that time would be random. But that can be done. People know how to do this. It's a very nice thing. In fact, I think that probably follows from what Michael has done already. Exactly. So, in fact, that would be a nice example to just do the Poisson distributed times. But it doesn't modify things very much at all. Okay? And so, I claim that this is a reasonable way of defining an effective diffusivity. And it's remarkably useful in the sense that people often have synthetic data that they got off some velocity field from the ocean or something like that, something which is a bit noisy, something which is not quite good enough for solving partial differential equations on, but maybe good enough to put some particles in and pushing them around. Or perhaps the particles themselves are flow trajectories that you got in the ocean. So you have, people have these big spaghetti plots of trajectories of floats. There's places like the Gulf of Mexico where people have released hundreds at once. And so you can follow all these particles, and you make some assumptions. They're not independent, of course. If they're far enough away from each other, they become essentially independent, right? But when they're close, you have to be careful. They're not independent. But people do this all the time. They take their floats, they assume that they're undergoing random walks, and they fit a capital K to this just by looking at how far they've gone, what is their mean squared displacement as a function of time. There's lots of caveats to this, right? Correlations I've mentioned. There's also the fact that the Gulf of Mexico is not infinitely big. And so if you try to fit your squared displacement to a linear time curve, it's probably not going to work forever. And we'll see that again in the examples I'm going to show you in a second. So there's some there's some educated guessing to be able to do this effectively. But it's a remarkably useful, poor man's way of finding an effective diffusivity to just look at some particles. Works great, actually. I mean, ideally, you've got the luxury of homogenizing a PDE and all that stuff, but in practice, you often can't do that. Okay. So how does this relate to the PDE? Well, if these particles are uncorrelated, right, and if I zoom in far enough, then I can imagine a cloud of these particles. Oops. I can imagine a cloud of these particles, right? Large number of such particles. And if I put enough particles there, I can compute their density, right? I can compute how many particles per square inch, or something like that, probably per square centimeter. This is a metric country after all. I think there's like 2 or 3 countries in the world that use the imperial system still. There's the US and like Eritrea or something. It's not a very big group, but the US will never change, of course. I'm Canadian, so I know metric. But I've just gotten used, you have to learn to talk down to them, Any Americans here? Wow, no Americans. Huh. So from this, I could get a density of particles, right? I would compute a concentration of my particles by just binning, and that would be a rough approximation of my theta of xt. Okay? Now, in practice, that's actually very hard to do. You need a hell of a lot of particles to be able to get anywhere near a reliable concentration field. But just speaking out of, as a principle, this is the way you would reconstruct a concentration field. And then, if some things, go your way, this cloud of particles, this should be capital theta, really. Or no, this should be little theta. But if I approximate it, if things are kind of uncorrelated in this case, and if you can kind of have the right limits. So what are the right limits? Meaning you need to be zoomed out enough that this cloud looks, you don't see the individual particles, right? You're seeing a kind of distribution. You need to wait for a long enough time that often there's some short time effects, right? Like particles might be heavily correlated at short times, and you have to wait a while for things to develop. So usually those are the things you want to wait for. You want to be zoomed out enough, and you want to wait long enough. Those are usually the 2 biggest constraints to being able to assign an effective diffusivity, right? I mean, you can imagine if I'm watching a colony of ants on the ground, for very, very short times, most ants are going in a straight line. So if I try to compute an effective diffusivity based on one ant, it's not going to work very well. But if I wait, they're going to start turning, and they're going to start wandering around. Or I could use an ensemble average over the ants. it's likely the ants are all moving in different directions. So even for short times, often I can get a pretty good diffusivity if the ants are independent, right? So there's a lot of assumptions there. But again, these things work remarkably well in practice if you're not too choosy. And people do this a lot. Okay. Right. So I'm getting close to doing my numerical experiments. So let me introduce the flow that I would like to, the map that I would like to study to show you some examples. So in the mixing community, there is one map that we love for simulating simple, for showing simple examples, or even studying as its own system, and it's called the sine flow. Possibly it was Rapier-Humbert who introduced this to the fluid dynamics community. I'm not so sure. It's essentially a version of the standard map, so it's really much older than that, but I think Ray really popularized it. And Jay Sukatme, who was speaking a few days ago, wrote several papers where they used the sine flow to show some very nice things happening in the advection diffusion equation. So what is the sine flow? It's very simple. You take a two-dimensional domain and you hit it with a shear. A shear is a flow a shear flow is a flow that only varies in a direction perpendicular to its direction, right? So a shear flow is not allowed to vary in the direction of motion. So here the flow is in this direction. I'm just showing you a sketch of how the flow is acting. So this is a box, and I've got some sine function, and the sine function is pushing particles in some direction proportional to, say, the x, the sine of pi x or something like this. Okay? So I'm going to write this more precisely. I'm going to say that the velocity field, I'm going to call it the horizontal part, is some amplitude times sine of 2 pi ky over L, where L is the size of my box. I guess my box goes from minus L over 2 to L over 2 in this picture, and same in the other direction. And then the other component of the velocity field is 0. Everybody knows how to tilt their head, right? Just everybody tilt your head. Now, I don't need to because I drew one of them, and I'm going to draw a second one, which is in the other direction. Because if I just use this, it's going to be relatively boring. It's not completely boring to study mixing in a flow like this, and people have done it. Basically because shear flows actually do occur a lot in nature, especially near boundaries, right? If you have a flow in a boundary layer, you're forced to go, you can't have any, you typically don't have much variation in direction of motion, but you have to vary very quickly in this direction because of the no-slip boundary condition, right? By the way, I think this is due to Feynman. What is the best argument that the no-slip boundary condition exists? Like, if you have to explain to your mom why there's such a thing as the no-slip boundary condition, because it's counterintuitive, right? Why should fluid stop at the surface? And I think Feynman gave this example. Fan blades get dusty, right? So that, to me, is the best example of the no-slip boundary condition. They get very dusty. What? Fan blades, like if you have a ceiling fan or something, the blades get very dusty, right? If there was a slip velocity, it would wipe off the dust. But even though the fan is turning very fast, it still gets dusty. So that's a very good argument that there's such a thing as the no-slip boundary condition. So it tells you the flow near the fan, of course, is going to be very much a shear flow. And that's exactly what turbulent modeling does, is model everything as shear flow. There's the Prandtl equation and stuff like that. But, sorry. So this is the horizontal part, and I drew, I guess, the vertical part, which is going to be complementary. There it is. Okay? So I've got two flows, and individually they're kind of boring. One of them is the horizontal. The horizontal goes like this, and the vertical goes like this. But the thing that makes them interesting is that you're going to pulse them. You're going to alternate these two flows. Okay? So I'm going to apply this for times, not 0. Well, let me write 0 for now. And then tau is the period. And I'm going to apply the other one for tau over 2 less than t less than tau. In other words, the period of my flow is tau. Sorry, I used t over there, but now it's tau, because there you are. So this is one period of my flow. Flow horizontally for half a period, then flow vertically for the other half of the period. The reason why this is such a good flow is that we can integrate the trajectories analytically at each step. Right? If I solve for x dot equals, if I solve x dot equals UH, right, that's two sets of equations. That's x dot equals U sine 2 pi ky over L, and y dot is equal to 0. So because y dot is 0, that means that y is constant here, and so I can just integrate and write that x is x0 plus y0 times tau, and y is y0. In other words, the new value of x at the end of a period is the previous value times this factor, whereas the value of y is unchanged. And then rotate. Tau over 2. Thank you. Thank you, because it's half a period. So if you put this on the computer, you can simulate a gazillion trajectories in a fraction of a second because it's a map. You don't have to integrate any ordinary differential equations. Which takes us to I can do this, right? Which takes us to the numerical simulations. Okay. Oh, is that the right screen? Can we do this screen? Yeah, sorry. That's not on my computer. All right, from this side? No? I'm just trying to entertain the crowd while we wait. Come on, we can do a wave. Come on. You go like this. And then, yeah. That's a sine flow right there. That was a pretty... Yeah, this is a completely broken sine flow. There we are. Okay. Thank you very much. So, example. So let's start. This is a sine flow. This is my initial condition. Yeah, the screen gets narrower. Do this. And so this is my initial set of points. It's a gazillion points. I don't know how many, but it's a lot. And now I'm going to hit it with this map. So this is once, twice. So at first it looks like it isn't doing very much. But like many chaotic systems, actually, one way in which it gets very chaotic is by the periodicity of the boundaries. So, see what happens? But it doesn't look very chaotic, does it? I mean, things are not happening in a very fast way. And there's a reason for this. This is with very small parameter values. So this is with a very small value of u. Okay? And if you look, sorry, it's under there, but if you think for a small value of u, right, you've got a map, and the particles move very little, okay? So you're actually building an ODE integrator, and what you're actually doing is tracing some simple streamlines for a constant stream function. So the particles don't move in very exciting ways because they're just locked to the streamlines of some steady flow. Okay, it's in fact a symplectic integrator because the map is area preserving. Okay, so that's the supremely uninteresting case. So let's do my example 2. Start again. And now the difference, let's see. I don't remember if I think I had a bit of noise in the other one. So D is the noise, L is the periodicity of the domain, T is the amplitude is the length of the period. So I guess U times tau is T, is some measure of the amplitude of the map. Okay? And iter is measuring the iterations. Oh, maybe I need that. I don't know. Okay, so let's do it. The center, okay. Oops, I always need to focus that window. So now you can see the noise, right? I've put a little bit of noise so you can see the thing gets noisy. So now I'm adding a little bit of diffusion at each step to help it along. So there's two reasons for noise right now. There's the map itself, and then there's a little bit of extra noise that's added at the end of each step. So it looks very similar to the previous picture. I guess this might even be the same parameter values, but you can see the noise is helping it along a little bit, right? The particles get a little bit more fuzzed out because of the fact that there's a little extra noise added to the trajectories. But it still looks a fair bit like the regular system, but if you wait long enough, eventually it kind of tends to reach an equilibrium, but it has a hard time penetrating these rolls, right? Which I won't have time to go into. Okay. Let's do another example. Let me just look, where's my iPad? Ah, there it is. Just make sure that I haven't forgotten to say anything. Yeah, so a bit of noise. Okay, this third example is going to be where I crank up this capital T, which is U times tau, right? It's the length of my steps in a way. It's the distance traveled by the particles in the sine function. So now things should move faster. Whoa. So it's completely chaotic, or almost completely chaotic, except for some regular islands. Okay, so when you crank up the parameter value, it mixes much more rapidly. And now, even without, this has no noise, right? But even without noise, it starts to approximate some random process much more rapidly. Okay? Right. Okay. So now, I'm going to do the same thing again. I'll take the, there will be this same advection, but now we'll add noise on top of that. And as you saw, it went very quickly this time, right? Let me do it again, just quickly. But things happen extremely rapidly. At first, I grow a little bit, but then the kind of exponential growth in my flow takes over, and I stretch my filament very rapidly. Okay? But there's no noise, so this filament is essentially infinitely thin, right? So, and then it's just kind of random. It's no longer a filament, really, because I'm not evolving a continuum of particles. But it would be a filament if I could evolve an essentially exponentially large number of particles. So now I add a tiny little bit of noise. So what do we expect? So again, it should look like a filament, but now it's like the first part of my talk. The noise I've added is like a diffusion, and it should fatten the filament to some degree. Okay? So it should look like a mixture of a chaotic system with a little bit of noise. So it's actually a fair bit of noise, because even after one step, before it was a tiny little segment, but now it's a big blob. Now if I do it again, so let me do, I think this is the right one. If I quit, it's going to ask me now to measure the width of a filament. So I click once, I click twice, and notice that it says, I measured the width at about 0.05, and the estimate is 0.1, meaning given the properties of this flow, the balance between diffection and diffusion should be roughly at 0.1. I thought it should have been better, but maybe it's... Oh, sorry. So then this is the same example, but with a much smaller diffusivity. See, the diffusivity is 10 to the minus 6, so now the filament stays much thinner. And again, I can try to measure the width of my filaments. Roughly. And so now the estimate, again, based on the properties of this flow, says that it should be roughly 0.01, and my measured by clicking is 0.008, so it's about 20% off. So again, the balance between the exponential stretching and the diffusion creates these filaments, and by measuring this width, we can say something about the flow. Of course, if we don't know the noise or the stretching, we can't determine either, but we can at least determine a combination of the two. Okay. Great. So these observations were more for the first part of the lecture. Now, for the effective diffusivity, I'm going to change things a bit. So now I'm going to take, the period is 0.5, so it's a little less chaotic. I've got some noise. Okay, so it looks a lot like an example that I've done before. So let's just iterate it and see what happens. So it stretches exactly like we did before. It makes a filament slightly fat because I've got a bit of noise. So now what if I tried to back out an effective diffusivity out of this by doing an ensemble, an average of the squared displacement of my particles? Okay? So I would get a graph like this. There it is. So these are various averages of x squared and y squared, and also the correlation between x, y for this particular. And capital X is actually it's x squared plus y squared. So it's the distance that a particle has traveled. But you can see it doesn't look really good, right? The distance, you could think that it's got 2 points, which, two iterates that you could call linear, right? 3 points at the very beginning. Let me use the pointer here. So was I using the wrong one? Or does it just shut off by itself? Probably shuts off by itself. Oh, okay, thanks. So that's what I mean, right? If you were very generous, you could say, this is linear. So why is it doing that? What's the problem? Why can't I fit a diffusivity here? Any idea? It's because the box is too small, right? This is my Gulf of Mexico, meaning my particles start to spread, but immediately they hit the fact that the domain is periodic, and now squared displacement doesn't mean anything because it's no longer growing. So it settles to some, oscillatory value that doesn't say much. So basically the system is, roughly speaking, well mixed, and there's much more you can say about it. So in order to make the system, to make things a little bit more appropriate for computing an effective diffusivity using this method, I'm going to take several copies of my domain now. So instead of using one fundamental period of my sine flow, I'm going to grow the box and do it again. So now it's allowed to spread and reproduce itself over several copies of the same domain. And if I do the same calculation as I just did, hopefully it'll look a bit better. Why isn't it showing up? Maybe I shouldn't have closed the window. Let me just start over from the previous one. So that was that one. There it is. So it's still not looking great. So this should grow linearly. And again, maybe it does for a little while, but again, it hits the edge of the Gulf of Mexico, and there's no way for you to back out an effective diffusivity out of this. Yeah. Okay. So now let's make it even bigger. So look at this one. Now I've made a bunch of copies of my domain. So now I'm allowing the particles to spread out. I'm basically hitting them, it's as we're saying, now it's a periodic flow, and I've essentially made the box semi-infinite now, so I hope my particles won't reach the edge of the box too soon. And now I should be able to back out a pretty good value of the effective diffusivity by fitting a line through what I see. So let's test this out. I don't want to go too far, right, because it's going to saturate again. Well, it doesn't matter, I guess. We'll see it on our plot. And there it is. See, there's some initial transient at the beginning, there's some uncertainty. It remembers my initial condition a little bit at the beginning, but after a while, look at this beautiful slope. So you could fit a slope through this, and the slope of this line would exactly be twice the effective diffusivity. Actually, it would be 4 times the effective diffusivity in this case, because it's the sum of x squared plus y squared. So you get 2 factors of 2D diffusivity. But the slope of this should be twice the slope of that. You see there's a slight difference. These should have the same slope. And again, that's some memory of the initial condition, right? It's only the slope that we're interested in. The fact that these two things have a slight offset here is not important. And notice by the correlation between x and y is 0, right? There's no, except for some, it oscillates a little bit. It's not exactly 0, but there is no correlation between x and y. I should say the homogenization picture, the basic diffusion equation that you would derive if you try to do the homogenization theory for this system. And by the way, for the system, you can do the homogenization theory exactly. There's no real difficulty in doing the homogenization theory. But see that this is kind of a diamond shape, right? Whereas the homogenization theory only knows about Gaussians in some sense. So at least at leading order, right? So you'd have to use higher correction in homogenization theory to start capturing the fact that this thing is actually skewed. The Gaussian statistics don't tell you everything about the shape of the distribution. It just tells you the leading order of behavior, but it doesn't tell you everything. And you would have to work harder. If you went to higher order in the homogenization theory, you could start to capture these deviations with a more complicated homogenized equation. And I think I may be out of examples. Yep, that's it. Thanks. Look at that, I ended up with 2.